NanoHub U, online instruction.
Hey everyone, welcome to lecture 2.7. So we're continuing with the concept of S matrices that have periodicity. And so before we'd actually written down an eigenproblem for coefficients of E and H fields in the presence of diffraction within layers. And I mentioned that there's not only an eigenproblem, but a generalized eigenproblem. And so we can write the generalized eigenproblem in this form. And then that gives us a simpler orthonormality condition that's automatically satisfied. So we can either use a regular eigensolver or generalized eigensolver for these sort of problems. And in this problem, once we have the phi x and phi y, then we can fairly simply write the H fields in terms of phi x and phi y times these coefficients a and b. And then these a and b coefficients relate also to the parallel H fields. And you can actually write down a and b for the E fields in a similar way. And so both H and E fields are all kind of coming basically from your solution to this eigenproblem. And then, of course, much like we discussed previously for S matrices, there's interface matrix for these problems, but we need to extract the A and B coefficients, which I just mentioned. So the interface matrix, again, much like the earlier case with the S of P or whatever, we can write it as I in this case. And so we write it as I of L plus 1. So that's like right at that borderline between the L and L plus 1th layer. And so it's basically the quotient of the matrix that goes in front of L plus 1th layer and divided by the matrix of the Lth layer. And so we basically write it like this. And so if we actually plug in the expressions for ML and ML plus 1, then we get something like this, which depends on the capital phi, which is a composite of the lowercase phi x and phi y, times this omega squared minus script k term that we mentioned earlier, bracketed by the q's, times this 1 minus 1 minus 1, 1 term in the first term, and then the second term is a little simpler, which is the capital phi transverse times omega squared minus script k times phi L plus 1 times the 1, 1, 1 term. Okay, so although it's a bit complicated, it's definitely numerically soluble. And then we can kind of recall that this is similar to what we had done previously in S matrices. So we feel like we're in pretty good shape in terms of that, but it's a more generalized approach because we're including like multiple diffraction terms. So in any case, what we can do now is, because we have an iterative solution, we can basically start with what we had 2 slides ago, and then use the compositing method to combine everything. And so you can see that that allows you to construct individual elements of the S matrix for L plus 1th layer in terms of everything that you'd calculated for the Lth layer. And of course, the elementary starting point at the very beginning is just the identity matrix, right? And so we're just kind of adding on to that. And of course, you can actually put this into software, and then you can solve it numerically, right? So that's very doable. And so in this particular case, this is from the Whitaker and Culshaw paper. They basically picked a relatively simple structure, which has air, and then it has 2 periodic layers, which have different refractive indices with the air gap in them, and then a uniform dielectric layer, and then a back reflector. And from above, it actually has triangular pattern. And then you can actually analytically approximate the Fourier transform of the epsilon in the lateral directions. And so that may help a little bit with numerical accuracy. And then you can actually calculate the reflectivity as a function of photon energy, or alternatively the frequency. And you can see basically that as you add more elements in the diffractive directions, which oftentimes you just think of as plane waves, then you actually get increase in accuracy at first. As you go from 3x3 to 5x5, you get rid of this spurious dip at 1.6 EV, for example. But you see that overall, like, the solution is actually fairly stable as you go to a larger number of plane waves, which shows that, at least for this example, it seems to work pretty well. And of course, it can be experimentally validated as well. So in the next lecture, we'll talk in more detail about some results that we can get from S matrices.